This episode is sponsored by Brilliant. We so often talk about building spaceships to visit and colonize new planets, but what about making a spaceship out of a planet? So today we're back to the Generation Ship series to discuss building spaceships that are of a planetary scale, or even outright moving entire planets between stars or even galaxies. And incidentally, if you're new to the channel, welcome to SFIA, probably the only place on the internet where a serious discussion about moving entire planets would qualify as fairly mundane. Why would you ever want to move an entire planet? That's a good question, but it turns out that we might have a few good reasons. First, we might realize that something is about to go terribly wrong with our sun, as will happen when it begins to run out of fuel and slowly heats up and expands, and we'll want to move Earth. Even as early as about 1 billion years from now, the sun's luminosity may have increased sufficiently to render the Earth uninhabitable. We've talked before about ways of extending a star's lifetime, but those are very time and labor-consuming tasks. Moving a tiny rocky planet like Earth is, comparatively, a weekend project, so you might decide to just migrate Earth to a new, younger solar system. Of course, we could face a more immediate solar emergency, perhaps of an artificial variety, such as an artificial black hole being dumped into the sun. You could also imagine disputes resulting in a planet being kicked out of its native system. We'll discuss this possibility later on. However, the most likely scenario under which you'd want to move a planet would be to serve as a colony ship. Something we noted earlier in the series, in the million-year arc, is that for very long voyages, such as to another galaxy, you need vast ship space and resources, enough to be stable and redundant for timelines longer than any civilization has lasted thus far, let alone any machine we've built. We do, however, have an example of a spaceship that can last billions of years. It's the Earth. We don't really know what the minimum size and mass of a ship needs to be to survive very long journeys, beneath which it can break down mechanically, genetically, or socially, but we know Earth will do the trick since it already has. Is it even possible to move a planet, and how would we go about doing it? Well, it doesn't violate the laws of physics. There are a few challenges to overcome, but it turns out that moving a planet is fairly easy and really just involves the brute force application of vast amounts of energy. Moving a planet on human timescales is, however, another story, and the first of our challenges. Planets aren't really designed for rapid acceleration, even less than an O'Neill cylinder converted into a spaceship, which we found out was quite a pain earlier in the series in exporting Earth. Consider, the moon exerts gravity on the Earth. It's about 60 times further from us than Earth's radius, and about an 80th of the mass, so it exerts about 3.5 micro-Gs of acceleration on us compared to the Earth's 1 G. If it's on the opposite side of the planet from you, you're about 3.5 millionths heavier than normal. If it's above you in the sky, 3.5 millionths lighter. Yet even this tiny force and acceleration is still enough to cause the tides, a significant disruption to the surface of the Earth. The Sun, 400 times further away but much more massive, actually does about double that, and sometimes the two will be in the same direction and combine forces to about 10 micro-Gs. We know the Earth can handle an acceleration on par with this since it does it every day, but going much higher would potentially cause a lot of severe tidal effects as water and air migrated toward one side of the planet. You could mitigate this somewhat with engineering like coastal walls. That's a big project of course, but small compared to moving a planet. But you probably can't take this too far since you'd also have to worry about the tectonic plates, mantle, and core shifting around on you, and that would be much harder to deal with. Still, you probably can do a lot better than 10 micro-Gs, but for now we'll assume that's the maximum acceleration the Earth can handle. To put 10 micro-Gs into intuitive terms, it takes about 1 day to accelerate an object at this rate to the same speed as 1 second of 1 G acceleration would take. Remember that 1 G is the acceleration you experience when you fall on Earth. It takes about a year of accelerating at 1g to get to about light speed, so it would take 100,000 years to reach about the speed of light at 10 microgs, or 1,000 years to get to 1% of light speed. That, by the way, is still way faster than a standard Shikata thruster can push a star up to interstellar speeds, and again you can push it faster if you do some heavy modifications to deal with tidal issues. If you wanted to move your planet 10 light years away, and you did it under constant acceleration, it would take about 1,000 years to hit the midway point, and your maximum velocity at turnover would be 1% of light speed. You'd arrive 2,000 years after you left. That's actually not bad for moving a planet, but a more conventional spaceship able to handle higher accelerations would seem preferable. And you could build a planet's surface area worth of O'Neill cylinder ships using a lot less mass than a natural planet has. However, if you're moving a planet because you want that specific planet elsewhere, this might be a viable timeline. The longer the distance of the voyage, the less acceleration rates and times really matter. Push out to 1,000 light years, 100 times further away, and you'd hit a maximum speed of 10% of light, and take only 10 times longer to arrive, 20,000 years. And if you wanted to go 100,000 light years, which is to say across the entire galaxy, that would get you pretty close to light speed, and that would be a 200,000 year journey, assuming that we ignore special relativity and time dilation for the moment. That's only twice as long as a conventional spaceship would take, even one with no organic crew members that can handle lethally high acceleration rates. For distances beyond that, at the intergalactic scale, acceleration rates are essentially irrelevant. Though for slower accelerations you would need longer distances to get up to speed, which will matter when we get to discussing where we are deriving the energy to accelerate our planet ships. Energy is a big deal in 3 other ways besides finding it for thrust though. First, planets are very good at storing heat, and a lot of the ways you'd be applying energy as thrust will lead to excess planetary heat. Earth normally emits a couple hundred million gigawatts of waste heat, mostly from absorbed sunlight, and even adding a few million more gigawatts of energy to that flow is going to have a noticeable effect on surface temperature. If you're trying to push Earth up to a decent percent of light speed, you're talking about adding somewhere around 10 to the 40th or 10 to the 41st joules of kinetic energy to it. If even a tiny fraction of that is being absorbed as heat, say 10 to the 38th joules, and you can only let a few million gigawatts extra into the system, or about 10 to the 23rd joules a year, you'd need a quadrillion years to push it up to speed without roasting your planet. So you either need to use a method that produces almost no new heat being absorbed by Earth, or you need a faster way to pump heat off. Fortunately, we have a slight edge here, since moving a planet through the interstellar void is going to result in a loss of sunlight. Even then though, it's too much energy to deal with in a reasonable amount of time, so you'll need to make sure you're absorbing very little of your thrust energy as heat. But you do want to absorb a bit of it because your planet is going to freeze otherwise. This would defeat the purpose of sending a living planet in the first place. Basically, you need to add the sunlight's worth of energy to the planet for the duration of the trip, since the sun is not coming along. This time anyway. We'll discuss moving entire solar systems in the next episode of the series, Fleet of Stars. Radiation and collision are our other energy concerns. The interstellar void has the potential for both of these in abundance when you're traveling at high speeds. Even in intergalactic space, and with good point defense to blow up objects in the way, these are going to be a bit much for a planet's magnetosphere and atmosphere to handle. You do not necessarily need to englobe the planet with some big shell though, since the vast majority of the dangerous stuff is coming from directly in front of you as you move. For instance, a big disk shield a bit larger than the planet could be placed in front, and you could probably set that up at a distance that made it look no bigger than the moon or sun in the sky. You could, perhaps, engineer the planet side of the shield to serve as an artificial sun, similar to what we discussed in the episodes in our megastructure series, Flat Earths and Making Suns. Of course, you'd probably want to bring the moon along if we were moving Earth. Conveniently, the moon could serve as a gravity tractor, which is the simplest method of moving a planet, though not ideal for high speeds. The moon orbits the Earth, and as mentioned pulls on the Earth too, indeed with the exact same force the Earth exerts on the Moon. If we push on the Moon with something, it will move, and if you push too fast, it will fly away from Earth, unless you're pushing it toward Earth. If you just want to push the Earth further from the Sun, you could push on the Moon when it's between the Earth and Sun, moving it away from the Sun but toward Earth. You would then push on it again when it was on the far side of the Earth from the Sun, again away from the Sun, but also now away from the Earth. That will cancel out its motion relative to the Earth, but not the Sun, and the Earth will have been nudged by gravity away from the Sun. The fastest you can push is equal to the force the Earth exerts on the Moon, otherwise it will fly off. But as mentioned, that's the same force the Moon exerts on the Earth, and as you'll recall, more or less the maximum acceleration the planet can handle, since we use the tidal effects of the Moon and Sun's gravity to place that limit. The gravity tractor approach certainly works, and isn't limited to using the Moon. For example, you could also send a string of asteroids by the Earth so that each exerted a small gravitational pull on the Earth as they flew past, or you could place large but weak engines in orbit around Earth that didn't produce enough thrust to break out of orbit, yet produced it for a very long time in only one direction. One problem though is that tidal forces cause tidal heating, and while gravity lets us avoid touching the Earth while we move it, that gravity is still producing some heat. So this method is fine for slowly moving planets further out in their own solar system with low inputs of tidal energy, but not ideal for moving a planet quickly, which would require high inputs of tidal energy. It is also heating up the Moon with whatever you are using to move the Moon, and that's not ideal either. So why not just apply force directly to the Earth instead of the Moon? That is an option, but it's problematic. In theory, you can put giant rockets on the Earth, or detonate nukes on the planet's surface, but the Earth has an atmosphere that's going to absorb almost all that energy as heat. This is the problem with using something like the fusion candle, our trick for moving gas giants, where huge platforms in the atmosphere suck in hydrogen, fuse it, and blow it out into space as propellant. We don't really care if those planets get hot, and they typically are fairly low density with more effective radiating surface area, so this works better for them. In fact, you could move a rocky planet of your choosing into a stable orbit around a gas giant that has a fusion candle, then when the fusion candle moves the gas giant, that rocky planet could come with it for the ride. Of course, you'd have to get the rocky planet into orbit around the gas giant by using some other method of moving it, which brings us back to the problem at hand. This is also a good approach if you wanted to move Venus further from the Sun and get rid of a lot of its atmosphere, which could be used as a propellant. But there are two engineering options for enabling the use of direct rocketry on a planet without heating the atmosphere. The first is to selectively remove the atmosphere in a small area around the rocket, which can be done by building a very high, thin wall, like a big rocket nozzle, that goes up above the atmosphere so that the rocket is basically in a vacuum. This is sort of the reverse of the partial terraforming trick that we often see in science fiction, where a high wall is built around the area intended for habitation, and that area is filled with air. Or, if you want to take this even further, you could actually englobe the entire planet, giving it an exterior spherical shell that had no atmosphere. Indeed, it's quite likely worlds looking to move beyond Ecumenopolis levels into being full-blown, mini-layered Matryoshka shell worlds might leave their top layers airless anyway, to facilitate off-planet transport and trade, so this would be a great option if they wanted to move their planets. The second option for enabling direct rocketry is related to the construction of the shell world. A giant sphere around a planet will require some sort of support, which could involve the active support system we call, appropriately, an Atlas pillar. It's basically a big space tower. You could just put your big rocket on top of a space tower that reached safely above the atmosphere. Of course, you're not using any sort of conventional rocket, not for moving planets. Chemical fuel ain't gonna cut it. Even fusion is only going to work if you've got a hollow shell world full of fusion fuel rather than molten metal, and even then, it will only allow speeds good enough for moving over interstellar distances. What we really want are technologies enabling travel over intergalactic distances, because we're interested in planet ships, not just moving planets we want elsewhere. A shell world around a world full of fusion fuel will provide shielding though. You could use a big external shell that wasn't just a thin shield, but a bunch of thin hollow tanks full of hydrogen, which is very good at absorbing radiation, and of course is a good way to store a lot of fuel, since mass arranged around something as a spherical shell exerts no gravity on the inside, or no net gravity anyway. A topic for another time, but you can use a very massive hollow sphere as a way to slow time down for those inside it. Regardless, such a shell full of fuel is a good way to store the fuel you need to slow down and run life support for that planet, which in this case is just artificial sunlight since it's an entire planet. We could also potentially use artificial black holes both as a power supply and a gravity tractor, either via smaller ones emitting Hawking radiation or bigger ones. We'll be looking at that more soon, but fundamentally, while they'd offer a higher velocity than fusion, as could something like antimatter if you can make a planet's worth of it and dare store that, they still have the basic problem of the rocket equation. You still have to carry all your fuel and pay the mass penalty for carrying it. We've spent a lot of time earlier in this series specifically talking about alternatives to avoid the limitations of the rocket equation, mainly light sails, laser sails, and the Stellaser. This is going to be the method that lets us really make planet ships viable for high speeds and intergalactic colonization, and inter-supercluster colonization, which you can probably only do with a planet ship. You don't necessarily need to use a planet, but a lower mass object like a moon exposes you to slow material leakage, as you have no decent natural gravity well holding things together. So you do have to be looking at things on that scale if you want to seriously contemplate trips that might take many millions or even billions of years without resupply. This is also one of the few cases where you might build a Stellaser all the way up into Nikola-Dyson beam Death Star levels of output. Converting an entire sun into a giant laser cannon sounds cool, but it's overkill for pushing a ship, and not the best way to weaponize a star either. You could just use a swarm of relativistic kill missiles, each accelerated by smaller lasers suitable for accelerating a normal spaceship. This is something we discussed a few times before, most recently in the Dark Force Theory episode if you want details on that. Lasers give us some big advantages, especially for slow acceleration. Mirrors can be made highly reflective, so they absorb very little of the light incident on them as heat, and indeed since we're accelerating quite slowly initially, we can bounce that beam back and forth many times to maximize the push. Now you can't just push a planet with a beam, not without melting it, as the atmosphere will absorb that light, but we've already discussed some options for dealing with an inconvenient atmosphere. We can install big mirrors on the ground in areas evacuated of air, we can put those mirrors on the moon, which then acts as a gravity tractor, or in orbit on hefty mirror platforms, potentially O'Neill cylinders to provide extra living room. We can hang them above the atmosphere but attached by space towers to the ground, or we can just build a big reflective sphere around Earth, which is bigger than Earth itself, so it also gives us more surface area to radiate absorbed heat away. Now, we've discussed pushing with lasers quite a bit before, and if you're bouncing the beam off the target, you need 1.5 gigawatts of laser for every ton you want to push at 1G, or 1.5 megawatts per kilogram. We want to do only 10 micro-Gs though, so we only need 15 watts per kilogram. The Earth's mass is 6 times 10 to the 24th kilograms, so we need 9 times 10 to the 25th watts of power. And conveniently, the sun produces about 5 times that, so we don't even need to take extra advantage of repeatedly bouncing the beam, and we can still get away with accelerating the Earth away at about 5 times our preferred rate. But if we did need to get the Earth moving quickly, we could pour the juice on, with full sun power and beam bouncing, and we could continue targeting that beam quite far out, since a planet is a pretty big target to keep a lock on. And of course if it has a shell, that target could be even bigger. It also means we don't need to be too picky about what other stars we use along the way, because we don't need to limit ourselves to the small fraction of stars as bright or brighter than our own sun. Furthermore, we could also be boosting our planet ship with lasers generated from multiple stars, since a target as big as a planet can be hit from many light years away. It also means you can send supplies along the way, as we discussed doing with colonial fleets in a previous episode. This is an entire planet, so it could have whole armadas of ships and habitats swarming around it that will jumping ahead or off to the side to colonize or set up new stellazers. Those smaller ships don't have to arrive around a way-stop sun ahead of it either, since the planet isn't stopping there and can push them down to speed with planet-based lasers as it flies by the star, so they can slap together another stellazer that can shoot the planet ship and push it faster. And you do want to be building more pushing stations along the way because that slow acceleration means your planet ship needs a very long laser highway to get up to cruising speed. If you want to get it close to light speed at that slow acceleration, it basically needs 100,000 years to get up to full speed, and would have crossed a big chunk of the galaxy during that process. It's also going to need the same to slow back down again at the destination, and you will be needing to send out vanguards ahead to build the necessary stellazers to slow it down. Now in truth, you probably won't need to build anything to get the planet ships up to speed, since odds are you're doing something like this after you've already colonized a lot of other systems and already have a lot of laser highways set up, though I'm sure you'd need to do some modifications since a planet ship decidedly qualifies as a wide load for your laser highway. You will still need to install new laser highway infrastructure for the deceleration portion of the trip, since presumably you're traveling to a new destination that hasn't been colonized yet, unless you're just shipping home bulk matter for building something enormous like a Birch planet, where the destination already has the infrastructure to slow the planet down. But amusingly, you won't always need to do as much slowing as you did speeding up. And with this we get to the real purpose of these things. We don't need them for colonizing our own galaxy, and even our nearer neighbors like the Andromeda Galaxy probably do not require this level of effort. A planet ship is not intended to colonize a single solar system, it's the ultimate gardener ship. Its purpose is to sow a line through a galaxy, leaving a thick trail of seed colonies in its wake. Indeed, you might not even try to stop it, just detach fleets of smaller colonial ships and push them to slower speeds with the planet ship's own lasers. These seedling colonies can then grow, build local stellazers, and send fresh boosts of energy and materials to the mothership for its continued journey down the intergalactic road. And they grow fast too, because you don't have to make colonies with just a few thousand people. Such a planet ship is probably an Econopolis peopled by trillions, who can easily dispatch 1 billion colonists and trillions of tons of colonial gear every decade or so as it passes by a good colony prospect. Indeed, it could be dispatching whole fleets to several systems in a fairly wide cylinder along its path. The planet ship need not stop in any galaxy, but can fly right through and get a course correction to intercept another galaxy down the road. This is where the planet ship excels, because it can contemplate multi-billion-year journeys, and there are many interesting destinations billions of light years away. And remember, all this stuff is moving away from us as the universe expands. Hubble expansion is about 7% of light speed for every billion light years of space between locations, so a ship hoping to reach a place 1 billion light years away needs to be doing more than 7% to ever reach it, and will arrive seeming to be moving slower. So if you send out a ship at 8% of light speed, it will arrive at only 1% of light speed, making it much easier to slow that ship down on arrival. Of course, it will take 100 billion years to get there, so you probably want to be going a good deal faster. Even just jumping up to 9% of light speed would halve your journey time. But we also don't necessarily care about ever slowing that planet ship down. Indeed, we might keep pushing it faster and faster, because we can always evacuate the population off in smaller ships if we want, as we've discussed, or just let it meander through the eternal void until it exhausts its onboard energy supplies for lighting itself during trips. But as we discussed back in the episode Dying Earth, this will be many trillions of years if its fusion fuel supply was a decent fraction of the planet's mass. But why limit ourselves to 9% light speed? With our ultimate planet ship accelerated up to say 70% of light speed, we could conceivably travel to galaxies that are currently 10 billion light years away, and at 99% light speed or higher, folks on the ship will experience relativistic effects, and time will slow down. The intergalactic void is quite thin, so these higher speeds are actually more viable than within galaxies. Again, a planet is a huge target for a laser, and with its mass and atmosphere, it can handle debris collision risks a lot better than a ship, because it can absorb a much bigger whack without being critically damaged, meaning its various point defense and detection gear won't have to work as hard at the same speed as a smaller vessel would. A smaller ship can't afford to miss even a single pebble at near light speed because it will detonate with the energy of a nuke. A planet can take that strike, and its sheer size can house much more detection gear, point defense, and whole armadas of tender ships and vanguards. Planet-sized ships need not be an actual planet though, merely things closer to that scale than the classic spaceship we see in sci-fi. Of course, when you're at the point that you're thinking about colonizing other galaxies, then planets or armadas in that general size zone are not much of a problem to source. You'd have billions to spare. Handy too, since there are billions of galaxies we could colonize this way. And this gives us the approximate answer to just how far off we can ultimately colonize without faster-than-light travel, at least 10 billion light years. Might as well think big. I always like pointing out that things like this, which are totally allowed under known physics, tend to be the sorts of things even sci-fi with lots of super science and clock tech won't touch as plausible. But moving planets is just raw brute force, not ultra-high tech, though doubtless more tech will help. And we might need to move Earth one day. It's a pretty unique place we'd want to save, rather than disassemble to be part of a Dyson swarm. Amusingly, you might even get kicked out of your home system by that Dyson swarm too. Planets have a lot of concentrated mass that represents a lot of perturbation on neighboring objects. It's manageable, but a hassle, and I could see the quintillions living in a Dyson swarm telling the billions back on Earth to either let them disassemble the place or pick up the planet and move. And more so for places like Mars or Venus that aren't humanity's cradle world. Marxit or Vexit scenarios might arise, and some place like Saturn or Neptune, which would already be pretty artificial and not dependent on sunlight anyway, might be willing to pack up and leave. We've talked about how O'Neill cylinders in a Dyson swarm might pack up if they didn't like their neighbors. These artificial worlds are already basically spaceships to begin with. It does make me wonder if future galactic civilizations might have the equivalent of solar divorces, where one side keeps the sun and the other gets most of the planets. Or heck, they might starlift a chunk of the sun off to take with them to make a red dwarf out of. We'll play around with moving solar systems next episode in the series though, in Fleet of Stars, and dig in more to the supernova engine we talked about last month in Dying Stars, along with starlifting binary Shikata thrusters, literal starships. I do suspect in most cases, a planet ship will tend to be a much more artificial thing built to planetary scale, but designed with space travel and higher acceleration in mind. But now we can see that true planet ships are possible, and put a whole new meaning on Spaceship Earth. So I was talking a moment ago about how this sort of endeavor is extreme even by sci-fi standards, but is actually a fairly simple process inside known physics. We can dream concepts like this up by knowing our math and physics, and so often can find truly amazing ideas that way. We rarely get a chance to dig into the details of how that math and science works here, and partially that's because learning them is best done at your own pace in an interactive environment, not by lecture. That's where our sponsor, Brilliant, really excels. They have a wide range of courses on math and science that let you pick the area you want to learn, start where you are ready to start, and practice that knowledge through interactive quizzes before moving on to more advanced topics when you are ready to. They also have daily problems in math, science, and engineering so that you can learn something new in 5 to 10 minutes every day. If you'd like to learn more science and math, go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can solve all the daily problems in the archives and access every course. So often on the channel we discuss dreams of more advanced technology in a bright future, But that's not everyone's dream, and next week we will return to the Rogue Civilization series to look at potential colonies settled by techno-primitivists, and we'll see how that might work out. The week after that, our episode will be on National Pet Day, and we'll take some time to look at what the future might have in store for our furry friends. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to support future episodes, you can visit our sponsors or donate to the channel on Patreon. Until next time, thanks for watching and have a great week.